So let's try this again. So please tell me if there is or is no sound.
No sound.
Titled Z3str4, a multi-arm string solver, which is work done with Murphy, Mitja, Dirk, and Vijay.
Can be a bit louder.
Just to get everyone on the same page about what string solvers are and what they are used for, consider a super simple Python function for checking if a password is strong enough, like the toy I have put on the screen.
Am I sharing a screen or not?
No, not. Just share the screen and make it a bit louder because
I'll
it's
try
very
again.
low.
Share.
Federico Mora, and I will be presenting our research paper titled Z3str4, a multi-arm string solver, which is work done with Murphy, Mitja, Dirk, and Vijay. Okay, so just to get everyone on the same page about what string solvers are and what they are used for, consider a super simple Python function for checking if a password is strong enough, like the toy I have put on the screen. This function takes in a string and has a few if statements for checking if the candidate password contains a number, if it contains an obvious substring, if it is long enough, and if it is just some other string twice. While this code is clearly a toy example, it should hopefully remind you of the kinds of string manipulations that software, and especially websites, do all the time. One of the really cool applications of string solvers, like the one I will tell you about today, is that they can be used to automatically reason about these same string manipulations that appear in programs all over the place. So that is to say, if we wanted to, for example, verify the piece of code on the screen, we could use a string solver to do that. So specifically, we could do something like take this piece of code on the screen and model it in first order logic modulo the theory of strings, like what we have done on the right here. Then we can take this logical model and give it to a string solver, like Z3str4, to automatically reason about the model. For example, we could use this to find bugs, maybe verify that there are no bugs, or for this toy example, maybe we could generate a password that satisfies all these constraints. And that's exactly what we'll talk about today. So we want to talk about an actual tool for solving these string constraints. In particular, we care about solving as many of these constraints as fast as possible. And just to be a little bit more clear about the kinds of constraints that we care about, we can handle things like regular expression membership queries. We can handle string containment predicates, linear integer arithmetic on the length of string terms, string concatenations and equations, also known as word equations, and much, much more. In fact, we cover the whole SMT-lib standard for strings, which we summarize in the grammar depicted on the left of the screen. Okay, so we know what kind of queries we want to solve, and we know that we want to solve them as fast as possible. And it turns out that the work we describe in this paper does quite well in terms of speed. So on the screen, you see our approach, Z3str4, plotted against the three best existing solvers, Z3str3, the Z3 sequence solver, and CVC4. And you have a plot where the x-axis represents the number of queries solved, and the y-axis represents the cumulative time taken to solve these queries. So basically, lines representing solvers that are closer to the bottom right of the graph are performing better. And what we can see is that over all of the existing solvers, over more than 120,000 queries, Z3str4 performs the best. For specific benchmark sets, sometimes we do less well than existing solvers, although still competitive. And for other benchmark sets, we do really, really well. But the thing that I want to highlight here, and the most important thing, is that we always greatly improve on Z3str3, which is the previous iteration of our tool. We believe that many of the insights that we're about to share and that you can see in our paper could similarly improve other solvers in this space. So let's get into how we achieve these results. The first contribution we'll talk about is a novel length abstraction-based solver, which we call LAS or LAS. The second contribution we will talk about is an extension to an existing arrangement-based solver, which we will call R. And the last contribution we'll describe is the overall architecture that combines the individual pieces of our approach. So first, let's talk about the length abstraction solver. At a high level, the length abstraction solver is an extremely simple refinement loop, which you can think of as guessing string lengths and then checking if there is a solution to the fixed length version of the input query. Guessing lengths isn't really a guess though. Instead, we use an integer solver to find lengths that are consistent with the problem at hand and move forward with that solution. More specifically, the first time we solve for lengths, we take in the input query, generate implied length constraints, and call a linear integer arithmetic solver to get a solution. Here on the screen, we have a possible input query on the left, an example. In the middle, we have the most simple implied length constraints. And on the right, we have one possible solution to these length constraints. In this talk, we'll be using purple variables as the integer lengths for this corresponding blue string variables. Once we have lengths for all the string variables in the input query, we can then generate a fixed length query or a character query. So in more detail, on the left, we have the original input query we saw before. In the middle, we have the length solution that we previously found. And on the right, we have the corresponding character query. Basically, the left column of this character query corresponds to the first word equation in the input, and the second column of the character query corresponds to the second word equation. You can think of each character variable as a bit vector. So then we take the character query that we generated and we solve it using an existing solver, like a bit vector solver. If this character solver says sat, then we actually found a satisfying solution for the entire problem and we're done. If the character solver says unsat, on the other hand, then we have to try other lengths. For the character query that we saw before, we would get unsat and we would be able to generate an unsat core like the one that we see on the far right. These three highlighted equations are an unsat core because they basically amount to saying that the character A is equal to the character C, which is clearly false. In the most naive setting, we could just block that string length that we generated before and then try again with a new length. However, we can often do better and we often want to do better. So sometimes we can learn general length constraints that block all equivalent unsat cores up to renaming, and this significantly trims down the search space. So for the original input query and the unsat core that our bit vector solver gave us, we will generate a learned length constraint. Specifically for the first equation in the unsat core, we can, if you squint your eyes, you can see that the last character of X will line up with the character A exactly when 2 times the length of X is equal to the length of Y plus 1. So if we want to avoid this alignment in the future, which we do, then we would learn to avoid that length, which we add to the column on the right. We have to do this for all the equations in the unsat core. So for the second equation, we get this new length constraint, which we find in a similar way by trying to avoid this alignment again in the future. And for the last equation on unsat core, we would get this third constraint on the right. So to make sure that we never get this same unsat core that you see in the middle of the screen up to renaming, we would assert the disjunction on the rightmost column. Since the last 2 learned components of that clause that we learned have to be true because they're implied by the original string query, we can simplify them away. In the end, for this input query and unsat core, we would get the learned constraint on the right, just 2 times the length of X does not equal the length of Y plus 1. We would then take this constraint and add it to the original set of implied length constraints and repeat the loop. If the integer solver says there is no length solution at this point, then we would return unsat. If some length solution does work and we make it all the way to the character solver and get sat from the character solver, then we would return sat, we'd be done. And otherwise, we keep going in this loop until one of those two things happen. And just to bring it all together very explicitly for a running example, one iteration of the loop looks like this, with the input query on the left, the guess at lengths in the middle top, and then the learned length constraint on the bottom. Okay, so that's the gist of the length abstraction solver. I just want to highlight really quickly before moving on that this works really well when every character query that you generate is only a conjunction of character equations. In this setting, when this is the case, the character solver is fast and we are able to learn these general lessons like the one that I showed in the example before. Now let's quickly talk about the arrangement solver extension. To understand the extension, first we need to get a sense of how the arrangement solver works in the first place. So at a high level, you can think of the solving process as recursively splitting equations into a disjunction of simpler ones until we either find that one of these disjunctions is satisfiable or we are able to block all disjunctions. So if we had a word equation like what we see on the screen, we would split it into three simpler ones. The first would have the length of m greater than the length of x, so we would split m and y into two variables each. The second would have the length of x equal to the length of m, so we could treat that original equation as two separate equations. And the third would have the length of x greater than the length of m, so we would split x and n into two variables respectively. We would then explore each of these branches recursively until we found one to be satisfiable, or we were able to reject all branches. The idea of the extension is then to combine this arrangement solver search with the length abstraction solver that we saw before. Specifically, there are some cases where arrangement generation can go into an infinite loop, so we interrupt that and call the length abstraction solver on those arrangements. Second, when some arrangement is found to be satisfiable, the character solving approach of the length abstraction solver turns out to be good for model construction at that point. So you can read a lot more about this in our paper, but that's all that I want to talk about the arrangement solver extension at this point. The final contribution I would like to talk about today is the selection architecture. This architecture uses the two solvers we just described along with the existing sequence solver inside Z3. To pick what solvers to run and in what order and for how long, the solver uses a mix of static probes and a technique we call dynamic difficulty estimation. In the interest of time, I will only describe one static probe, the conjunctive fragment probe, but you can read about the other pieces of the architecture in our paper. The conjunctive fragment probe is a context-free grammar, which is shown on the screen. For a given input query, we check if the input query belongs to the language defined by this grammar. If yes, then we run the length abstraction solver first. If no, then we run a different solver first. Now, if you remember from before, the length abstraction solver works really well when the character queries that it generates are conjunctions of character equations. This probe guarantees that every iteration of the length abstraction solver will produce these kinds of character constraints. So, for this fragment of string queries, the length abstraction solver is quite effective on its own. That's why we want to call it first. For queries outside this fragment, it is usually better to go with another approach, like the arrangement solver. Finally, on to the evaluation. We performed our experiments on an Ubuntu server using the Zalig-Vinder benchmarking framework. The timeout for every instance was set to 20 seconds. Overall, like we saw before, we do quite well. Z3str4 is able to solve more queries in less time, like we set out to do. For the length abstraction solver, we see that in the conjunctive fragment, the one that corresponds to the probe that I previously described, we solve more queries per second than outside of the conjunctive fragment, as we suspected. These high percentages that you see on the screen are partly due to dynamic difficulty estimation, which is really good at cutting off the length abstraction solver before it spends too much time, before it wastes too much time. You can read more about that in the paper. The arrangement solver also does quite well with the extension. So without the extension, we're able to solve around 72,000 instances in around 423,000 seconds. With the extension, we are able to solve 148% more queries in 61.8% of the time. And that's all that I have for you today. Thank you very much. Please make sure to check out our paper. And a special thank you to the reviewers that did an amazing job with our paper, and we are extremely indebted to. Thank you.
Thank you very much for the nice presentation, for the nice recording. We have some time for 1-2 questions. Please raise your hand or ask directly. Federico, are you with us to answer?
Yep.
Good. Okay. It seems to me that this approach is very similar to that given by Clark Barrett 2 days ago, and his invited talk, SMT domain-specific reasoning, and it was a theory of strings, and he presented some. Do you know about it? Can you relate it?
I'll have to double check. I missed that presentation.
Okay.
But...
Okay. It will be nice to see it. Another technical question. It seems to me that solving strings via arrangements is strongly related to unification modulo associativity, a theory the strings belongs to. And is it true? And the simplification from there are very similar to the unification, to those given by unification algorithms. Okay.
Yeah, I think you're right.
Can you comment a bit?
I think you're right, and we kind of went through like an exploration stage early on when we were building this tool to try different techniques, and I think I remember trying something like that. It's been a while, but I think the arrangements. One of the advantages of it is that the implementation turns out to be quite efficient, quite nice, and often we end up balancing sort of like what is kind of like a nice theoretical approach along with the implementation, which the arrangements turn out to be like a particularly nice one.
Why I ask that? Because there are algorithms that are using unification for solving. I'm not sure we know about that. There are some algorithms based on unification for solving.
Yeah, we're not using that internally, but
not yet.
That'd be something cool to look into. Yeah.
And yes, because the unification is infinitary, so I wish to know if there is some problems with that. Okay. Other questions? Please,
yes,
please.
I find a question in the chat, maybe.
Chat? I don't. Where is it? I don't see it. It's in question Q&A, but I'm not. I don't know what I cannot see it because.
I can read it out.
Please read it because I cannot see it. The Windows is very bad arranged.
Yeah, this is a question. Yeah.
It says maybe a naive question, but is there any work that compares or takes into consideration robustness for these SAT solvers modulo a distance measure? So thank you for the question. So I think by robustness you mean like performance robustness. Is that right? Maybe you can clarify. So yeah, maybe I'll answer it while maybe there's a clarification.
Okay,
But so we
Well,
didn't
by
measure.
robustness, I mean, sorry for the distance, but by robustness, I mean that now you have you generate a string which satisfies the given condition, the given formula, right? And now, if there are minor changes to the string is still satisfied by the given formula. So that is what I mean by robustness.
Oh, I see.
Yeah. So basically,
interesting.
that even some minor perturbations to the string will not affect the satisfaction of the formula.
Interesting. So I haven't pursued work like that. Off the top of my head, something that comes to mind is that there are some kind of like fuzzing approaches to to actually finding satisfying models, which would be doing these kind of perturbations. And I guess they would be extremely sensitive to this kind of robustness that you're talking about. But we haven't looked in that direction, but it sounds really cool. Interesting question.
Thank you very much.
Okay, thank you very much. We are a bit late. We have to move on. Thank you very much, Federico, for your presentation, for your answer. Very nice talk. Okay.